Okay, let's introduce some useful theorems with respect to duality. And these are maybe why we're interested in duality, other than kind of the interpretation of our dual variables as being shadow prices. So first off, the theorem, kind of weak duality, says that if we've got a feasible solution to the primal and a feasible solution to the dual, then the objective value, so this is sort of the objective value for the primal, and this over here is the objective value for the dual, that the maximization problem always has a lower objective value than the minimization problem. So I'm sort of assuming that the primal is a maximization and the dual is a minimization problem. Okay. If it's swapped, then actually these get swapped around here. But what does that mean? Well, if we find one feasible dual solution, it ends up being an upper bound for a maximization problem, which is sort of tells us we can't get any better than that, which is useful to have. Sometimes you don't need a full solution. You just need to know, well, how could it be in the best case, or maybe even beyond the best case in this case. But it also sort of lines up. There's some solution techniques where you're solving the primal and dual simultaneously, and the dual problem is a minimization problem that's getting lower, and the primal problem is a maximization problem that's getting higher. And so eventually you're trying to get them to meet in the middle. Okay. And that's actually the essence of strong duality. So not all types of optimization problems have strong duality. If they've got duality, they usually have weak duality. But strong duality says that if a linear program has an optimal solution, then so does its dual, okay? And their respective objective values are equal, okay? And so if there's a feasible optimal solution for the primal problem, then there's also a feasible optimal solution for the dual, and they have the same objective value. So sort of the best case for the maximization problem is also the best case for the corresponding minimization problem. And so with this sort of weak duality, you can kind of think of the primal problem as approaching the optimal value from below, and the dual problem as approaching that same optimal value from above. So complementary solutions is actually really a great tool for moving back and forth between primal solutions and dual solutions. So for every primal solution, there's a complementary dual solution. And here's how they're defined. Here are the formulas. But better than the formulas are those same formulas in words. So this quantity here is the difference of what is the right-hand side of the dual constraints minus the left-hand side of the dual constraints. And so this value here is the amount of slack that you have in your dual constraint, multiplied by your primal variable. And that has to be equal to 0. Now, if two things multiply together to give you 0, then you know that either this is 0 or that is 0, or potentially both are 0. But they can't both not be 0. Does that make sense? And so in words, the first one of these says that your dual slack times your primal variable equals 0. So if your dual slack is non-zero, that forces the primal variable to be 0. If your primal variable is non-zero, it forces the dual slack for the corresponding constraint to be 0. And we have the same thing going the other way. Dual variable times primal slack equals 0. So if a dual variable is non-zero, it forces there to be 0 slack in the primal constraint. If there's positive amount of slack in a primal constraint, that forces the corresponding dual variable to be 0. That one actually makes easy sense. If there's some slack in a constraint, then the corresponding dual variable is 0, which means that for all constraints where you have some slack, you get 0 for your shadow price, meaning that you wouldn't be willing to pay anything to increase that resource because you have slack in that resource already. Okay. So, and then a theorem related to complementary slackness essentially says that if you have a pair of complementary solutions to their primal and dual, And if both of those and if the pair is optimal for their respective problem, then they're both feasible for their respective problem. If they're feasible, then they're optimal. And so you only have to usually actually use it this way. You only have to check feasibility, and if they're complementary, then that gives you optimality. Okay. So every solution to the dual has a complementary solution to the primal and vice versa. If the pair of complementary solutions are both feasible, then they're also both optimal. Okay. And this complementary slackness allows us to find optimal dual solution problem and transfer back and forth between the dual and the primal. Okay. Let's see an example of this kind of complementariness, as well as another example of practice writing out our dual problem. So let's consider Geppetto's workshop. And so I'll pull that up. We had that kind of a couple pages back in the handout when we were talking about shadow prices. And let's go ahead and see if we can transform this primal problem into the corresponding dual problem. So first off, Geppetto's problem is a maximization problem. And so when we write out the dual, we're going to have a minimization problem. So minimize W, W is going to be equal to Y transpose B. Here, maybe actually, before I get there, let's make a note over here, primal, dual. The primal problem here has 2 variables, 3 constraints. 2 variables, 3 constraints. The dual problem is then going to have 2 constraints and 3 variables. Okay. So let's see. We're going to minimize Y transpose times B, which is going to be, let's take our right-hand side vector of 180, 40. And so we're going to have 3 variables for the dual. We'll call them Y. Actually, let's call them YF, YC, and YD. Because they essentially correspond to the finishing, carpentry, and demand constraints. And then the right-hand side vector for the original problem is 180, 40. And so this gives me the 100Y1 plus 80 YF YC plus 40 YD. Okay, so that's my dual objective. Now let's write out the dual constraints. And so that will be Y transpose times the A matrix. So YF, YC, and YD times the A matrix. The A matrix originally looked like 2, 1, 1, 1, 1, 0. Okay, so essentially reading off the 2, 1, 1, 1, 1, 0. The other way you can do this, and I'll often do this, is I'll sort of take this as a column here, and I'll label that Y1, and this as a column here, and I'll label that as Y2, and you'll see what happens in just a minute. Oh, no, this is sort of my X1 column, X2 column. Sorry, no. What I want to do is actually go the other way. So let's choose a different color. This constraint corresponds to Y1. This constraint corresponds to, or YF, YC, and YD. Okay. Don't know if that helped too much. But then since this is now a minimization problem, the original constraints were, or the original variables were greater than or equal to. And so then this becomes greater than or equal to constraints for all of them. And then what was originally the original objective vector of 3 and 2 is the new right-hand side. So writing this out and kind of multiplying this down, we get 2yf plus yc times 1, ycn plus 1 yd. And that will give us the first entry on the left side, and that's going to be greater than or equal to 3. And then we'll do the same thing for the second column over here, and that will give us yf plus yc plus 0yd is greater than or equal to 2. Okay, this constraint here, and here's maybe where I was getting ahead of myself here. I can read that constraint off as 2, 1, 1, all the coefficients of x1 here, and then the right-hand side is 3. So I see here I've got 2, 1, 1, and 3 for the right-hand side. This is the constraint, and maybe I'll label it in a different color. This is the constraint that corresponds to the primal variable x1, and this is the constraint that corresponds to the primal variable x2. Notice that if I look at that kind of column of everything multiplied by x2, I have 1, 1, 0, and then a value of 2 that then goes on the right-hand side. So 1, 1, 0, and 2 on the right-hand side. Okay. So that's sort of my methodology when I'm thinking about moving from primal to dual or dual to primal. Okay, now let's kind of think about what our optimal solution was to Geppetto's problem. So optimal primal. Okay, so the optimal primal problem had x1, and so kind of here I said this is the final tableau, and we read off that x1 equals 20, x2 equals 60, and slack for demand was 20, which gives us 20, x2 is 60, slack for finishing. I'll put the slacks in order. So slack for finishing, slack for carpentry, and slack for demand. Slack for finishing and carpentry, those were both non-basic variables, and so they're equal to 0. And then slack for demand, that was a basic variable and had a value of 20. Okay, now let's talk about essentially the complementary dual solution. Okay, so what did I say? Primal variable times dual slack equals 0. So any non-zero primal variable must have 0 dual slack to get to 0. Okay, so this first primal variable is non-zero. And so the corresponding dual constraint should have no slack in x1 constraint. Okay, and if there's no slack, then this x1 constraint here, if there's no slack, then we're right on the boundary. This inequality turns into an equality. And so that tells us that 2yf plus yc plus yd is not just greater than or equal to 3, it's exactly equal to 3. Okay. Let's do that with the second primal variable. It's positive, it's not 0. So that will tell us that there's no slack in the corresponding x2 constraint. So remember, x1 is number of soldiers and x2 is number of trains. And so this constraint here is really looking at the you kind of think of it as the value that you get from using each of these resources, and the value that you're putting towards trains. or for soldiers, and then for trains in the second one. Okay, and that the value that you're using in the resources has to be at least as much as the profit that you're getting from it. And that's the way you can interpret the dual constraints, is that the value that you get from an activity, or yeah, the value that you get from using those resources in an activity has to at least match the profit that you're getting from them. Okay, and so no slack in that one. So we know that YF plus YC plus 0YD equals 2. Okay. So here we've got that there. Now we're looking at the slack for the primal problem, and so now we're down to here, and so we know that primal slack times dual variables equals 0. Which tells us that if a primal constraint has 0 slack, then we really don't know anything about the dual variable. But if a primal variable has positive slack, then we know the corresponding dual variable must be 0 in order to make this equal to 0. So this one here, that since slack for finishing is equal to 0, that just tells us that the corresponding dual variable is going to be greater than or equal to 0. And so same here, YC is going to be greater than or equal to 0. These are sort of uninformative. Okay, not very useful, at least when you're going this direction. If you were to know the values of YF and YC were positive, then you'd know that pushes these to be 0. So they're maybe useful going back this way, but not very useful going this way. This one, on the other hand, since we've got a positive amount of slack in the demand for soldiers constraint, we know that YD has to be equal to 0. Okay, so if we wanted to find the dual solution that corresponds to this primal solution, we've actually got now 3 equations and 3 unknowns. So we've got this equation, and this equation. These two don't really give you any good information, but we've got 3 equations and 3 unknowns, and so that's actually a linear system that we can solve. This one being equal to 0 allows us to immediately go ahead and kind of cross that out up there. And then so these 3 pieces of information essentially give us the system that 2YF plus YC equals 3 and YF plus YC equals 2. Okay, so a system with 2 equations, 2 unknowns. If there is a solution, it's going to be a unique solution. And in this case, we know that it does have a unique solution. And well, we actually already know the values of YF and YC because we actually got the full tableau over here in the final tableau here. And we know that those are going to be the values up here. And so, yeah, if you didn't know that, you just solve this system. But if you know that, then actually all you're doing is verifying this. But it's pretty powerful that if you know a primal solution, you can always find a complementary dual solution. And that's true even if you're not at the optimal solution. Okay. And so this, if you go ahead and solve this out, maybe the easiest way would be to take row 1 minus row 2, and that would eliminate the YC variable, and that would give you YF equals 1. And then plugging YF equals to 1 in here would give you that YC also equals to 1. Okay, and so along with the fact that YD equals 0, that gives you your dual solution. Okay, so complementariness, you can use that in order to find a corresponding dual solution. And I guess one thing I didn't mention already is that if your primal solution, so if you got a complementary pair between a dual and a primal pair, if the primal solution is feasible, the dual solution is going to be infeasible unless they're, except for in the case where they're both feasible, in which they're optimal. And so maybe that's this sort of theorem here about complementary slackness. If you got complementary solutions and they both end up being feasible, then they're optimal. Okay. Most of the time, if you're not yet at optimality, then feasible primal solutions correspond to infeasible dual solutions. And your book goes into some nice detail in that and has a nice diagram that I encourage you to look up when it's talking about the complementary solution section. Okay. That wraps up this video and this example.